right? She has been a master teacher since 2007. Presently, she is an advanced chemistry teacher at Cornwall College, and she has worked at all levels of the examination process as moderator, examiner, marker, you name it. And so I just want to turn over the rest of the session to Mrs. Hall. And can we just acknowledge her if you can? Mrs. Hall?
Thank you very much, Dr. Taylor Campbell. Good afternoon, students, colleagues who might be here with us. And we will be looking at hydrocarbons. I've grouped them as hydrocarbons as it's alkanes and alkenes. And we will be focusing on that and then looking at some questions that are focused on our alkanes and alkenes. Dr. Taylor Campbell will manage the chat. You can make your comments, answer questions in the chat. If you need something explained, you can raise your hand and your mic will be open for you to do so, to ask your question. I will be closing my camera. Just wanted for you to see my face initially, and I close my camera now. If you are not speaking, please ensure, or not asking a question, please ensure that you keep your mics closed. All right. So as indicated, we're looking at hydrocarbons today. Objectives taken directly from your CAPE syllabus: identify homologous series of organic or carbon compounds, including your general formula. Describe selected chemical reactions of alkanes, namely halogenation, cracking, and combustion, and equations are required. Explain the steps. Explain the steps involved in the mechanism of free radical substitution. Describe selected chemical reactions of alkenes with liquid bromine, aqueous bromine, cold potassium permanganate, acidified potassium permanganate, hot acidified potassium permanganate, hydrogen halides, and we're looking at catalytic hydrogenation. And we are to explain the steps involved in the mechanism of selected chemical reactions of alkene functional group. All right, so before we get into the actual functional group, we're going to look at the two main types of bond fission that occurs for our covalent bonds. And this is important because we need to understand what happens in bond fission in order to understand the mechanisms of your reactions. So there are two types. You have homolytic fission, which is the breaking of bonds, which results in each atom retaining the electron that they contributed to the formation of your single bond. At the end of this process, free radicals are produced. Then we have heterolytic fission, which is the breaking of your covalent bonds again, and result in one atom retaining both electrons from the bond. And therefore you get ions being produced at the end of this process. So you get a cation and an anion being produced. Any questions on that? Please remember, you can type in the chat or raise your hand if you have any questions. All right.
No questions yet?
So that is clear. That seems to be clear. All right. Now, combustion is a process that both your alkanes and your alkenes undergo. So your hydrocarbons burn in the presence of oxygen to produce carbon dioxide and water. And we have a general equation for the combustion of hydrocarbons. So my general equation is CXHY, that would be my hydrocarbon, plus X plus Y over 4 oxygen, which will give us X carbon dioxide plus Y over 2 water. Now, how is it that they got this? And once you understand the basis for this, you can balance any combustion equation. So we are producing carbon dioxide, we're producing water when we burn the hydrocarbon. All of the carbon in the carbon dioxide comes from your hydrocarbon. And so that is going to be denoted by X. So the number of moles of carbon present in your hydrocarbon will determine the number of moles of carbon dioxide which will be produced. All right. With respect to hydrogen, we have all of the hydrogen in your water molecules come from your hydrocarbon. But each water molecule has, or each mole of water molecule has in it 2 moles of hydrogen. It means, therefore, that overall, the amount of water that is produced is going to be half the number of moles of hydrogen that is found in your hydrocarbon. So technically, you get Y over 2 times 2, which gives you back your Y. It's going to be half the number of moles of hydrogen.
Remember to mute your mics, students. Mr. Harris?
All right. Now, how do we get the X plus Y over 4? In your carbon dioxide, you have O2, and that O2 must come from your oxygen that you're burning your hydrocarbon in. And therefore, if an X is the coefficient, it means that we need X as a part of the coefficient for our oxygen. In water, we have 1 mole of oxygen per mole of water molecules. However, we have O2, as in our oxygen molecules, not oxygen atoms. And therefore, it means that your Y over 2 oxygen atoms would be a half of Y over 2 of your O2. And that Y over 2 times a half gives us Y over 4. All right. So this is our general combustion, and we will meet this again when we look at alkanes in detail. All right, so alkanes is our first set of hydrocarbon, and just as revision, because of course, the information here with respect to general formula, and the nature of our hydrocarbon is information from the CSEC level. And so the general formula for alkanes is CnH2n plus 2. That's the general formula. Now, our alkanes are called saturated hydrocarbons. That is, each carbon has the maximum number of hydrogen bonded to it. So there are only single bonds in alkanes. Because each carbon has the maximum number of hydrogen bonded to it, or alkanes, sorry, are fairly unreactive. So there are really and truly only 3 major reactions that your alkanes will undergo: combustion, cracking, and halogenation. And we're going to look at these 3 reactions in detail. All right, so combustion. Alkanes, as we said before, when hydrocarbons combust, they form carbon dioxide and water. Alkane is our saturated hydrocarbon. And therefore, when alkanes combust, they will form carbon dioxide and water. So our example here, propane. And we're applying the general equation, which was introduced 2 slides before, previous to this one. And so we're going to get, as our coefficient, working out our coefficient for oxygen, the 3, which would have been our x, plus y over 4, so that would be 8. Sorry, made a mistake in doing this. Ooh, I was rushing, made a mistake and just saw it. So let me do the correction right here. So that's y over 4. So that would give me and this is going to give me x. Oh, sorry about that. And this is going to give me x carbon dioxide, which would be my 3, plus my y over 2 H2O. So the balance equation is C3H8 plus 5O2 to give 3 CO2 plus 4 H2O. Check the balancing to see if I'm correct, and you can use your thumbs up to indicate if you agree with the balanced equation. Finish checking. Is it correct or is it incorrect?
Okay, they're saying correct.
Okay, so it is balanced. All right, and that is what you need to know for combustion. That is what you need to know for combustion. Now, cracking. Cracking is the decomposition of long chain alkanes into shorter chain alkanes and alkenes. And generally, you will find definitions which will say decomposition using heat, because both types of cracking require relatively high temperatures. Now, there are two types of cracking. You have thermal cracking and catalytic cracking. In thermal cracking, you utilize temperatures of 700 to 900 degrees Celsius, while in catalytic cracking, you utilize temperatures of 400 to 500 degrees Celsius, and the catalyst is a mixture of silicon dioxide and aluminum oxide. Any questions? All right. So our examples. So there are two examples here. C10H22, and that can be cracked to give C8H18 plus C2H4. So your longer chain alkane, C10, is going to be broken into a shorter chain alkane, C8, and your alkene, C2H4. Please note, the number of carbons must add up to the original number, to the number of carbons in the original molecule. The number of hydrogens must also add up to the original number of hydrogen. Second example, C14H30, and here we get C8H18 plus C4H8 and C2H4. So in this case, you get an alkane and two alkenes. Again, if we add up, 8 plus 4 is 12, plus 2 gives us back our 14. 18 and 8 is 26, plus 4 gives us back our 30. So if you get a cracking equation to do, just to double check, ensure that you add your carbons and your hydrogens in order to ensure that you are not overstating or you're not giving products that are not possible. So you want at the end of cracking to have at least one alkane and an alkene, or you could get a mixture of alkane and more than one alkene. All right. Any questions? Any questions, Dr. Taylor? Not yet?
Not yet. Students, remember, you can raise your hand if you're not understanding, and we'll allow you to ask your questions as well and post your responses in the chat. Okay, Miss.
All right. Oops, sorry. All right, so the final reaction of our alkanes, is halogenation. Now, because alkanes are saturated hydrocarbons, they will undergo substitution reactions. You cannot add anything to an alkane. You have to substitute onto the chain of an alkane. So your alkanes will undergo substitution reactions. The mechanism for halogenation of our alkanes is our free radical substitution reaction. So if it's free radical, what type of fission is taking place. We looked at fission earlier. What type of fission would be taking place?
Homolytic bond fission.
Go again?
I said homolytic bond fission.
Yes, correct. That's how we produce our free radicals. All right. Now, there are 3 stages in your free radical substitution reaction. These are initiation, propagation, and termination. All right. Now, your initiation reaction. In your initiation reaction, the bonds are split by homolytic fission using UV light to produce free radicals. And we are looking at the reaction of ethane with chlorine. That's our example. And so 2 possible initiation reactions are given here, where chlorine will split to give 2 chlorine free radicals. Or your ethane, one of your carbon-hydrogen bonds can split and you will get an ethyl free radical and a hydrogen free radical. All right. Are there any other possible initiation steps for this reaction? We're looking at ethane with chlorine. Yes, no, maybe so.
No response. Come on, students, respond. If someone says not that I recall.
Looking at it, is there anyone that is there
someone
a
says
possibility?
no more. Someone says no
Right.
more initiations.
Right.
No.
You
Right.
need to be confident in your answer. All right? Because we're starting out with just these 2 molecules as our reagents. So you can only have initiation taking place with these 2 reagents. Very good. Propagation is the next step. Now, in this step, a free radical and a molecule reacts to produce a new free radical and a new molecule. So for this step, free radical and a molecule is going to give you another molecule and another free radical. All right? So there are 2 examples here. Anyone can tell me if there are any other examples? Are there any other possibilities?
Okay, someone is saying no.
These are the only possibilities. Let's go back and look at. There are 3 different free radicals that are produced. Have we utilized, make a note. Have we utilized, sorry, Have we utilized all of those free radicals? Somebody in the chat.
Okay, someone saying another hydrogen radical can be formed.
How? Want to open your mic and let and state
Ms.
how it is?
Can raise your hand if you want to answer. Serena. Okay, no response.
We have not utilized anywhere on this page as yet C2H5 free radical. What could the C2H5 free radical react with? Anyone? I've given you half of the answer already. Anyone to finish it?
It could react with a chlorine molecule.
And I would get?
C2H5Cl and a chlorine free radical.
Okay, thank you very much. All right. So we need to ensure that we look at the possibilities. A question may just ask you for one propagation step. It may ask you for 2. It may ask you for 3. So we need to ensure that, because once we have 3 different free radicals, it means that those 3 different free radicals can be utilized in the propagation step. All right? The final step is termination. And this occurs when 2 free radicals combine to produce a molecule. All right, so I have 2 possibilities here. Are there any questions on the 2 possibilities that I have before I continue?
Miss, you can get one more.
I know we can get more, not just one, more than one, but are there any questions? Okay, so here I have my ethyl free radical reacting with my chlorine free radical to give me a product molecule. So my chloroethane, all right? But my second reaction, I have a chlorine free radical and another chlorine free radical combining to give me chlorine molecule, which is not a product, but a reactant. Why would this be possible? Anyone wants to tell me why this would be possible? Nobody wants to tell me why this is a possibility?
Miss, can you please repeat, please? And thank you.
Chlorine free radical with another chlorine free radical is giving me back a reactant molecule, not a product molecule. Why would this second reaction be possible any at all?
Oh, you're talking about like what needs to be present? I'm not following.
No, why is it that this reaction is possible? Because this is not a product. It's a reactant that we are basically producing. Why would that be possible?
Okay, we have some responses in the chat if you want them. So
Alright.
somebody's saying, is it because the reaction is reversible? Why would it not be possible? They both have an unpaired electron, so the reaction can continue taking place, and that's a question, to go to the start of the process.
All right. If you have a reaction mixture, please remember that there is nothing really separating the free radicals from each other. And there is always the possibility of any two free radicals in your reaction mixture coming together in order to form a molecule. It means, therefore, that there is the possibility of producing your reactant molecules because the free radicals can recombine in that way. Also, there is within your reaction mixture, it's not that all of your molecules will undergo initiation, then you have only propagation taking place in your reaction vessel and then only termination. No, all of the processes are taking place simultaneously. And therefore, as I said before, any two free radicals can come together to form a molecule. All right? Yes, because they're highly reactive. They have this unpaired electron. They're basically in their atomic state, and they don't want to exist as atoms. They want to bond so that they can be stable. All right? Everyone is clear on this? What could be another termination reaction taking place?
The C2H5.
A C2H5 radical and another C2H5 radical, producing C2H5, C2H5.
Or C4H10, yes. That's a possibility. And of course, hydrogen free radical with the chlorine free radical to give you your hydrogen chloride. All right? Any questions? Anyone not clear?
Someone is asking if it is true for all radicals, the fact that the two radicals can combine because they're highly reactive.
Yes.
Okay.
Free radicals, and that is why, and to relate this to your module 3, that is why you get destruction of ozone. Remember, you would have learned in module 3 of this unit on the atmosphere about free radicals, the chlorine free radicals reacting with ozone, causing destruction. And this is the reason they are so highly reactive and they want to react that they are going to find oxygen, cause oxygen free radicals to form, and then you have the combination and you get all of these possibilities in the atmosphere. All right. Oh, sorry, I saw a question that
Someone is asking, can there also be two hydrogen free radicals combined to form H2 gas?
I glimpsed it and clicked it off. Yes,
Right.
Yes, that is a possibility. All right. Any questions on alkanes and the reactions of alkanes? So we looked at combustion, we looked at cracking, we looked at halogenation. Any questions? All right, no questions. So everyone is clear on this now. All right, let us move to our second hydrocarbon, groups of hydrocarbon or alkenes. General formula, CnH2n. All right, seeing something in the chat. Oh, okay. CnH2n. Now, your alkenes are unsaturated hydrocarbons with at least one double bond. All right? And they're unsaturated because not every carbon has the maximum number of hydrogen bonded to it. So that double bond reduces the number of hydrogen that the carbon can bond to. All right? What was the question? The free radical can take an atom from anywhere in the compound. I'm not clear. The question, I'm not sure what the question is asking. If it's a question, Kadia Bailey, you can open your mic.
Someone says not anywhere, I believe. Okay, the person who asked the question, do you want to raise your hand so you can ask?
Right, because I'm not completely clear as to.
Yes, I was asking if there's like a free radical on a compound, if it can take an atom from anywhere in the compound. So if you have C2H5 plus a Cl, but there's other radicals there. So I'm asking if other radicals can join anywhere. So you can take a H or so from the compound itself.
All right, so if I have two C2H5 free radical, you said, and I have a Cl free radical.
Yes, miss.
That's a termination step. So it's going to it is going to react and be added to the compound. Are you talking about the substitution aspect? If it could substitute for any of the hydrogens?
Yes, miss.
Yes, for not the carbon, but it can substitute for any of the hydrogens.
Okay, thank you.
Okay. Abraham?
Thank you. Good afternoon, Miss.
Good afternoon.
Taking a look at the properties here, could you remind me what we said about the reactivity of alkanes, whether they're very reactive or fairly?
No, fairly unreactive. Alkanes, they're fairly unreactive. So they only undergo 3 reactions: combustion, cracking, and halogenation. And technically, the real reaction there is halogenation.
Okay, thank you, Miss.
All right. Okay, any other questions on alkanes? All right. Oh, I see something in the chat. Let me check before I move on. Okay, someone was answering. All right. Now, alkenes are fairly reactive and they will undergo addition reactions. And the addition reaction is because of the double bond, which can be broken. Now, the high electron density in the double bond region makes them attractive to electrophiles. Can anyone tell me what is an electrophile? You can type it in the chat or raise your hand. What's an electrophile?
Someone says electron loving.
All right, it is electron loving.
Electron rich species.
No, it's not the electron rich species.
Somebody says positively charged species that attack an electron rich area of the molecule.
Right.
It's a deficient, well, I guess they're meaning electron deficient.
Deficient. Mhm.
General carry a positive charge and attracted to an electron-rich compound. A positive or I guess, or partial positive species that's attracted to electrons. Not
All right.
necessarily positively charged though, that's somebody else.
Right. All right. So an electrophile, remember philes, lover of electrons. All right. So it is an electron deficient species. So it's not necessarily that it is positively charged. It does not have to be positively charged. All it has to, the species, all it has to do is to have some sort of electron deficiency. And therefore would like to be in the presence of an electron-rich species or area. So someone said, electron-rich species? No. An electron-rich species would be a nucleophile. So the electrophile is lover of electrons. Opposite charges attract. Therefore, if it loves electrons, it must have some sort of electron deficiency itself. Everyone is clear on that? I can get yes, no, maybe so in the chat, or a thumbs up before I move on.
Okay, yes, they're saying yes.
Okay. Want to hear from the person who said that it was an electron-rich species, just to make sure that you are clear.
Okay, Tishia Riley, are you clear? Please.
Please just say yes or no. If you're not clear, then open your mic so that I can clear up the misconception.
Miss Riley?
Did we lose her?
Let me check. Cannot see any response. Tishia Riley, we're checking to see if you're clear on why it is not electron-rich species, but electron deficient. Okay.
All right, not getting a response.
Okay, all right, you can continue.
Right. All right. So, as indicated, we have several reactions to look at for your alkenes. Now, alkenes undergo electrophilic addition. And it is addition again because we have the double bond and the carbon does not have the maximum carbons that are involved in the double bond, does not have the maximum number of hydrogen or species bonded to it. So you can add to it. You can add to the molecule, and it is electrophilic because of the electron-rich area in the region of the double bond. So here we're looking at the reaction with bromine, liquid bromine. This mechanism is particular for liquid bromine and to some extent aqueous bromine. But we'll look at aqueous bromine after this. Now, if you look at our bromine molecule here, please remember that bromine has temporary dipoles in it. Bromine, two bromine atoms, so there is no separation of charge really. And if we are looking for an electron deficient species to be attracted, then it means that something must create that deficiency in this molecule. And that is why you cannot say it is a positively charged species, because Br2 is not positively charged. Br2 is a very charge neutral species. What occurs is that as Br2 approaches your double bond, you get some amount of induced separation of charge because the high charge density starts to repel the electrons in your bond. This gives you a temporary dipole within your molecule, and you get a slightly negative end and a slightly positive end. The electrons from the double bond, and please note, my arrowhead is a complete arrowhead. What does that tell me? Let's see if we remember.
It's
the
two
rules.
electrons traveling.
That is 2 electrons that are moving. So both 2 electrons are going to now move towards forming a bond with this slightly positive bromine, and both electrons from the bond within the bromine molecule will go to my bromine with a slight negative charge. When all of this takes place, I get the formation of an intermediate carbocation and a bromide ion. So I get an anion and I get a carbocation. And the carbocation is because the 2 electrons, remember that 1 electron from this double bond, well, sorry, 2 electrons would have come from each of your carbon. When you break the double bond, what is happening is that those 2 electrons are taken to form a dative covalent bond with bromine. Everybody remembers about dative covalent bonding? So the carbon, this carbon in this case, is providing both electrons to form this carbon-bromine bond, which means that my carbon right here has effectively lost an electron, and that leaves it with a positive charge and gives us our carbocation. The carbocation is our intermediate. It is not a very stable species, and therefore the bromine now comes in with its additional electron from the previous, from the bromine that it was bonded to, and donates 2 electrons to form a dative covalent bond here to give us our final product. So we would go from ethene to 1,2-dibromoethane. Any questions?
Okay, no questions at this point.
All right. So everyone is clear on the mechanism for electrophilic addition.
Yes, may I ask you to repeat specifically what you're saying about dative covalent bonding
Okay,
in
let's
middle step?
start.
Thank you.
All right. So let's go again. Conditions, Adrian. For bromine, There are no specific conditions because, sorry, the halogenation of alkenes can take place in the dark. That's how reactive it is. So unlike your alkanes that required the UV light that was stated for the initiation, here, this can take place in the dark. All right, so let's go again. Both electrons, 2 electrons from the 4 that are in this double bond will go towards forming a bond with this bromine that would have lost one of its electron when the 2 electrons from the bond with this bromine goes to the bromine with the slight negative charge. It means, therefore, that this bromine is 1 electron deficient. It has 1 less electron than it should. In forming the bond, 2 electrons are donated towards this bond formation because our arrow has a full arrowhead, which indicates the movement of 2 electrons. So, because the carbon is donating 2 electrons towards the formation of the bond, it is effectively a dative covalent bond. The second carbon is going to be deficient of 1 of its electrons. So it has a positive charge. Your bromide ion here, because right here, what type of fission is taking place right here?
Etherolytic.
Repeat.
Etherolytic fission.
Heterolytic.
Right. So it's heterolytic fission that is taking place here. And we're effectively forming a cation and an anion. So the anion, the bromide ion, has this extra electron that it got when it broke, when this covalent bond broke. So now it can donate 2 electrons, full arrowhead, to the formation of a bond with my deficient carbon. So effectively, my 2 carbon bromine bonds are dative covalent bonds. Any clearer, or did I leave you in the dark, in the same thickness of darkness?
Yes, that's very clear now. Thank you.
Very clear? All right. Are there any questions in the chat about the reaction of liquid bromine with our alkene?
Not seeing any questions.
Okay, so let us move on. All right. So reaction with aqueous bromine. This slide looks very busy, but let us break it down. So propene with bromine water. All right. So this is our aqueous bromine. Now the step 1 is going to be the same as the previous slide. You're going to get electrons coming in from the double bond to form that dative covalent bond with your bromine that has the slight positive charge. The bromine bond breaks and give you a bromide ion. So that is fine. That is what is going to take place. So you have your carbocation. Now, once your carbocation is formed, because it is aqueous bromine, so you have Br2. Oh, sorry, I left off the 2. I'll have to do that correction. Because it's Br2 in the presence of water, We are going to have bromide ions there, but we also have water molecules that can effectively contribute an OH to the formation of a bond. So you will, up top here, you can get 1,2-dibromopropane, which is the same product that you would have gotten if you used liquid bromine. The difference here is if your water molecule, because it's dilute, a dilute solution, so we have present lots of water molecule. Remember, the oxygen in water has 2 lone pairs. And so these lone pairs can go towards forming that dative covalent bond. And of course, you lose a hydrogen ion. Your OH right here, you are going to get those 2 electrons going to the oxygen so that it does not feel any deficiency, and you get H plus being formed. So in this case, your product would be, because we're looking at propene, your product would be 2-bromo-propan-1-ol plus HBr. Ask your questions. Ask your questions. No questions?
Somebody wants you to go over the second step?
Yes.
And
Not a
just
problem.
to indicate that we're halfway.
Oh boy. All right.
All right.
No, it's not necessarily because OH minus is more electronegative, but it's a dilute solution, so you will have lots of water molecule. Lots of water molecule, because technically, look here, your bromide ion has 1, 2, 3 lone pairs that can be used for that dative covalent bond, while your oxygen has only 2 lone pairs. All right. All right. So up top is the same steps that would have taken place on the previous slide. So the person who wanted me to go over the second step, I am taking it that it is not that first part. Yes, water can act as both a base and a nucleophile, depending on the conditions. All right. So I'm assuming this is fine because this is what we did previously with liquid bromine. So our step 1 is the same. We form our carbocation. Our water molecule is there and it has lone pairs. And therefore the lone pairs on the oxygen can go towards forming a dative covalent bond with your deficient carbon. At the same time that it is forming this dative covalent bond, the oxygen hydrogen, one of the oxygen hydrogen bond is being broken by heterolytic fission. So oxygen keeps both electrons from that covalent bond, and H plus is going to be given off. So you would get your alcohol being formed along with your hydrogen ion. And of course, Br minus would have been left over from the heterolytic fission of Br2, so you get an alcohol plus HBr as your result, as your products. Any clearer for the person who needed me to go over it? Yes, only one of the bromide is used. Only one. In this second mechanism, only one bromide is used. So you get alcohol plus HBr. In the first mechanism, you just get the one product of the dibromo-substituted alkane. All right. All right. So we have our reaction with HBr. We have our reaction with HBr. The mechanism is the same. It is your electrophilic addition mechanism. Here, we know that our hydrogen is going to be less electronegative than our bromine, and bromine holds on to those two electrons to give us Br minus. The electrons from the double bond come in and they form a dative covalent bond with your hydrogen. You get your carbocation intermediate and you get your bromo alkane. So it's the same mechanism. Any questions? No questions. All right. Now, addition to an asymmetric. So what we have been looking at for the HBr, we looked at a symmetric. It was symmetric. Everything was the same all around. So it was a symmetric molecule. Now we're going to look at addition of HBr to an asymmetric molecule. And asymmetric meaning that the double bond does not sit smack in the middle of your molecule. You have a difference in the number of carbons attached to the two carbons involved in the double bond. That's what asymmetric means. All right. So you have a difference. Now, this is where Markovnikov's rule comes in. Markovnikov's rule comes in. All right. Sorry. So this is an asymmetric molecule. Notice that this carbon has two carbons bonded to it, while this carbon only has one carbon bonded to it. All right. Now, when HBr comes in, my hydrogen can go to either of these carbons. But the rule states that your hydrogen will add to the carbon that will produce a tertiary carbocation. That is, it will add to the carbon that has more hydrogens bonded to it. And why is this a tertiary carbocation? Because it has, look, it has 3 carbons bonded to it, no hydrogens. And this carbocation is more stable than your secondary, which would be the alternative down here. And that is because it has attached to it what are called more electron donating groups. So your CH3 is an electron donating group. And this carbon is going to be stabilized by these electron donating groups that will be pushing electrons towards your deficient carbon. So when you have an asymmetric alkene, what your hydrogen from your HBr or from your hydrogen halide will add to the carbon in the double bond that has the most hydrogens bonded to it. All right? Any questions on that? Any questions on that?
Not seeing any questions.
All right. So your major product, sorry, you will get some of this secondary product, but the major product is going to be your product which comes from your tertiary carbocation. All right, no questions?
No questions.
All right. All right, hydrogenation, addition of hydrogen in the presence of nickel at 150 degrees Celsius. Hydrogenation, addition of hydrogen in the presence of nickel. You could also use platinum at 150 degrees Celsius. And this produces the corresponding alkane. Now, this reaction is of industrial significance because this is the reaction that is utilized to convert vegetable oils to margarine. So the margarine that you buy, chiffon and Gold Seal and Country Crock and all of those margarine, this is the process that they use. Your oils are generally unsaturated, long chains with unsaturated chains. And so to convert them to solids at room temperature, you saturate them by adding hydrogen in the presence of nickel or platinum. All right. Now, you also have hydration taking place. Hydration of your alkenes, and hydration of alkenes produce the corresponding alcohol. Hydration of alkenes produce the corresponding alcohol. Now, this is normally done in the presence of an acid. And the reason why you want that acid is because you need to protonate the double bond and form your carbocation. So you protonate the double bond, form the carbocation, and then effectively your water molecule goes in, forms your intermediates. Remember, water does not want to have 3 bonds, and then it is going to lose, your water molecule loses a hydrogen to reform the H+, which is your catalyst. All right, so you get protonation, then nucleophilic attack by water, and then deprotonation to give you your alcohol. So those are the steps for hydration. Any questions? No questions? All right. Oops, sorry. All right, final reaction of your alkenes.
Miss,
Yes,
go back
sorry,
to slide one.
go back.
Yes, please.
Yes,
Okay, thank you.
all right. So the final reactions of your alkenes, reaction with acidified potassium permanganate or acidified potassium manganate 7. And there are two conditions. We generally use cold dilute or hot concentrated. Now, when you use cold dilute, it is an oxidation. When you use cold dilute conditions, you get the diol. You get the diol being produced. So room temperature, dilute, acidified potassium permanganate, you're going to get the diol being produced. Your syllabus says that you don't require equations, you just need to be able to state, but this is chemistry, I like equations. All right, so this is what would take place for your cold dilute. Now, when we have hot concentrated, there are several things that can take place. So hot concentrated, we can generally, what happens is that you're going to get the diol, and then you get cleavage of the molecule to produce your acid. In this case, because of where the double bond is, you produce the carboxylic acid from this end of your molecule. So you would have gotten diol, and then you get cleavage and you produce the carboxylic acid, and this end will give you your carbon dioxide when you oxidize fully. And that is why the conditions are hot, concentrated.
Someone is asking you to go back to the previous slide.
Oh, sorry. Cold dilute.
Okay, all right.
All right. All right. So this would be propene. All right. And we would get ethanoic acid and carbon dioxide. Now, here I have 2-methyl-butene. All right, so my double bond is here. Initially, of course, I get my diol, and then I'm going to get cleavage taking place. And because of the groups that are attached, I get carboxylic acid, because it's really a secondary alcohol with a primary alcohol. When you cleave and you get the carboxylic acid from the primary alcohol, oxidation, so it goes aldehyde then to carboxylic acid. And here, because essentially it's a secondary alcohol, it stops at your ketone. So you would get acetic acid and acetone. All right, any questions?
Not at the moment.
Okay. All right. The third scenario is not really one that is of importance. They don't generally give us dienes. So we can ignore the third scenario here. What is of importance? The equation, these first two equations. All right. Any questions on those? Any questions on those? No?
No questions.
All right. I think that's the end of, yes. All right. So I'm going to stop sharing so that I can share now the questions.
Someone is asking if you're not supposed to get water for the first one.
As well?
First one. Yes.
No.
I'm not there. I don't know water.
No. Let me go back and look at it. Make sure. For the first one, so it was C3H6, and I end up with, yes, water. Water is also a byproduct, but I was looking at the carbon. So yes, you do get some water, but the water, generally, that is not what is of importance. It's the acid and the carbon dioxide, but yes.
Okay, someone is asking for cold KMNO4 in acidic conditions, you get diol. So what do you get for hot KMNO4 in acid?
Oh, that was the last slide. And it is dependent. Let me go back and share. Let me share again. I'm switching over. These are the possibilities for hot. Generally, we use cold dilute and hot concentrated. But once it is hot, even if it's dilute, then eventually you will get these as your products.
Someone is asking if the slides will be shared.
Yes, I'll send them to you again, Dr. Taylor.
Okay, no problem.
So I'll send it to you at the end. All right. Any other questions?
Not seen anymore.
All right. So stop sharing that, and let me. All right. Are you seeing?
Yes, yes.
All right. Oh, went too far. All right. I think this is 2018.
Okay, just before you start, someone's asking if the carboxylic acid was formed due to oxidation of an aldehyde.
Yes. What happens, remember, it takes place in stages. It's just that we go to the final product. So really and truly, it's the diol that is formed, but because the oxidating power is so great, you get cleavage, of the molecule, and you end up with your diols being two alcohol molecules, which are then, if it's a primary alcohol, you go to the aldehyde, which is then further oxidized to the carboxylic acid. If the alcohol produced is a secondary alcohol, then it goes to the ketone, and there's no further oxidation. Because remember, your ketones are not easily oxidized. All right? All right. All right, so I think this is 2018, if I remember correctly. So it says figure 1 shows the reaction sequence of an organic compound A producing compounds B and C. Please note, and this is why it is important not to just look at alkanes and alkenes in isolation, because remember that these compounds will react. They can be the starting of a series. It can be the starting of a series or a reaction series or a group of reactions. All right. So here they said, identify the reaction mechanism leading to compounds B and C. What's the reaction mechanism leading to compound B?
Electrophilic addition.
Electrophilic addition. All right. C, because you're going to need to know it anyway for multiple choice.
Nucleophilic substitution.
Nucleophilic substitution. All right. Draw the displayed formula for each of the following compounds, and they want for B and C. They want for B and C.
All right, so for B, you're gonna draw but compound A, but with the Br being attached to the carbon number 2. Okay, it's gonna be the carbon number 2, since it has the less amount of hydrogens, and then the H being attached to the other carbon.
Go again.
Okay,
That
you're gonna
sounds
have,
like Rodin.
yes, it is. Miss.
All
Yeah,
right.
you're gonna have
Go again,
um,
Rodin.
compound A
Markovnikov
again, right?
rule.
But you're gonna have the H being attached to the carbon that has the more hydrogens attached to
Which
it.
is carbon number?
It's carbon number 3. No, carbon number. Yeah, carbon number 3, isn't
So
it?
that carbon number 3 is going to have what? The H or the Br?
It's gonna have the Br.
Right. That's not what you said at first. That's why I asked you to go
Okay.
again. All right, so carbon number 3. So this is carbon 1. I hope you're seeing my cursor. Carbon 2. So the double bond is between carbons 2 and 3. Markovnikov rule states that the carbon that has more hydrogen attached to it is going to be the one that the hydrogen from your HBr is attached to. So carbon number 2 would get a hydrogen attached to it, and therefore Br would go on carbon number 3. So when you draw out your displayed formula, you're going to have CH3, CH2, CH3Br, meaning a methyl group is attached to that carbon, and Br is attached to that carbon. Then CH2, CH3. That is what your bromine is going to look like. Sorry, your bromo alkane is going to look like. So you're really and truly drawing, you are drawing the structural formula for 2-bromo, 2-methyl pentane. 2-bromo, 2-methyl pentane. That's what you're drawing the displayed structural formula for.
Excuse me, Miss. Didn't we say that the bromide was going to go on to the third carbon?
Yeah.
So wouldn't it be three bromo, 3 methyl?
3, sorry. It's the end of the day, sorry. So 3-bromo, 3-methyl pentane. Thank you so much. And you are awake. That is a good thing. All right. They want the formula for C. Where would my OH go? What is OH? Because it's a nucleophilic substitution.
Which is a nucleophile.
So OH, where's it going to go? What is it replacing in my molecule?
The halogen.
It's replacing the Br. So it means, therefore, that the OH is going to replace the Br, and so it will be on carbon number 3. So we get 3-methyl pentan 3-ol. That's the compound we're drawing. 3-methyl pentan 3-ol. All right, somebody wants me to show the formula. All right. Let me see if I can. The problem that I have is that this is not a touchscreen device. So it becomes very tricky to try and use the whiteboard. It's not my best feature.
Someone is asking if it's required for you to know the mechanism to go from B to C.
They wouldn't well, they say alkane and alkene is what they're focusing on. But as I keep telling my students, it's going to be very difficult for them to focus on alkane and alkene alone, because organic chemistry is such that they are so related. The homologous series are so related to each other, and you generally have all of these mechanisms that are related to each other, and they like to give schemes of reactions. So technically, you shouldn't need to. Note, I said technically.
Same person is asking if you can explain the mechanism, I guess, when you return.
The mechanism to go from B to C, nucleophilic substitution. All right. All right, so B would look like this. And they wanted displayed formula. So they are expecting you to draw it out. This would be CH2 and that would be CH3. All right. Any clearer for the person who?
I think they wanted from B to C as well.
Right. So B, so are you understanding B, the structure of B?
Sorry, Terry-Ann?
Yes. All right, so you, oh, could you repeat what you said about Markovnikov? Okay. All right. So the double bond, let me erase. And go back to my, oops, sorry. Did the wrong thing. Get back. Ah, totally. Did the wrong thing. Go back to my whiteboard.
Yes, yes.
All right. So my double bond would have been here in my original molecule that they gave you. So this is where the double bond would have been. So this is Markovnikov rule states that the hydrogen from the HBr would go to the carbon that has the most hydrogen bonded to it. So this carbon has one, this has none. It has only CH3. Ignore these two strokes that we have here. All right. When the double bond is removed, the hydrogen would go on this carbon and the Br would go on this carbon. All right. So that's how you get B. That is how B would be formed. So that's Markovnikov rule. All right. Now this is B. So going to C now. What is going to happen is I'm going to get, and please ignore my very crude drawing. I'm going to get the breaking of the carbon bromine bond. It is heterolytic fission, and therefore the 2 electrons will go to bromine. When the 2 electrons go to bromine, I am now going to get I need to get back the pen. Where do I get back the pen?
I think you deselect or something. Sure.
All right. I did deselected the eraser.
Right, and so you have to click back the pen now.
Oh, that's a spotlight. Oh boy. All right. So what is going to happen is that my OH, which is now, this would be a carbocation because I would have a positive charge here because this carbon would have lost its electron. So the carbocation is going to be formed here, and OH with its negative charge is now going to come in and form a bond with this carbon. So your OH would come in here and you would then get your alcohol being formed. All right? Person who was asking, undo, wrong thing. Person who was asking, do you understand?
Stania.
Okay, she said yes.
Okay.
All right. All right, let us go back to sharing my question. All right. So that would have taken care of displayed formula for B and C. Let's see if there was anything else. I think this question had other things that did not pertain to hydrocarbons. Let's see. Okay. Oh, they said using curved arrows to show the movement of electrons, write the mechanism for the conversion of compound A to compound B. All right. Write the mechanism for compound A going to compound B. All right, let's go back. Let's see if we can go back to the whiteboard so that person's. All right, so I have, let's do it like this. And this is my double bond. So you don't have to use the displayed formula because it's really the double bond that you want to highlight in your mechanism and to show the movement. And then this is C2H5. Right, yes. C2H5. All right, so it would be HBr. So we know that you need to show your arrow. And we know that this is going to come in. So that is the first step. So you need to show transfer of the 2 electrons to the Br to form your Br minus, and you need to show the movement of electrons from the double bond to your hydrogen. All right. Now, of course, this is then going to produce your carbocation. This has CH3. And your C2. Five. And you show your positive charge here. All right. So that is your carbocation. Your Br. Oops, sorry. So your Br minus. You show your arrow going to your carbocation, and finally, you are going to show the product. So this question is worth 4 marks. All right. So
Okay.
you get 1 mark. You get 1 mark for showing the movement of your the movement of your electrons to your hydrogen. You get 1 mark for showing the movement of electrons to the Br. You get a mark showing the formation of your carbocation, and you get a mark for the final product. All right. Any questions on this? Any questions on the mechanism?
Not seeing any questions.
All right. So we can go back to our question.
If you don't understand before Miss moves, indicate if you have a question for her with regards to the mechanism. Okay, not seeing any raised hand.
Right. Well, that is good.
All right.
That is good. It means that they are understanding. Hopefully that's what it means. All right. I don't think. All right, so that was the 4 marks. To this thing, oh no. This is alcohol, so this would not be. All right, I think we are moving next. No, this question is not. So we're moving next to. I think this is the question. All right, yes. This is 2015, paper 2. So propane is one of the major components of liquefied petroleum gas, LPG. Give me a second, let me move my, you're seeing the question, right? The petroleum industry uses a process to produce another alkane and 2 alkenes from propane according to the equation below. Identify the process represented by the equation. What's the process? What's the process?
That is correct.
Cracking. All right. State
what type of cracking?
That is where it now comes in. State the conditions at A. So A is right here. What would be the conditions at A? In the chat?
No responses. I think somebody thinking that you're breaking up, but I think it's probably their connection.
Yeah. Conditions at A? No
so I'm
response?
not sure how you would tell whether this is thermal or catalytic cracking.
Read again the statement. What does it say? Part 2. Note what I'm emphasizing. State the conditions at A.
Okay, so more than one condition, I suppose. Okay, well, since you're emphasizing conditions plural, I'd say this is catalytic. Therefore, the conditions would be 400 to 500 degrees Celsius. in the presence of silicon dioxide or aluminum oxide?
Mixture.
As in aluminum oxide mixture, that's what it is?
Yes, it's a mixture. It's actually both. Silicon
Oh.
dioxide
Oh, it's
with,
both of them.
yes,
Oh, okay.
aluminum oxide. All right. And that is why that word conditions is very important. It is catalytic cracking. If they said state the condition, then of course it would be 700 to 900 degrees Celsius, but they said conditions, which means that you have more than one thing happening here, and that is only with catalytic, where you have the catalyst and the temperature. All right, write the condensed structural formula for B and C.
Someone is asking if thermal cracking doesn't have a pressure requirement.
No.
What is required for thermal?
Thermal, 700 to 900 degrees Celsius. Oh, sorry, B and C. Remember what we're trying to do. So it must balance out. C3H6 and CH4. That's correct. So methane and propene. Methane and propene. All right, remember what the rule is. So we're starting here with 8. So that is octane. Is this octane? Sorry, we're starting with two propanol. Sorry.
6 carbons.
We're starting with 2 propanol. So it's 6 carbons in total. So we must have 6 carbons here. And we already have 1 alkene. So we know that something here must be an alkane, and we are going to get more than likely another alkene. So we have 2, so we only have 4 carbons to play with here. When we look at the hydrogens, we start out with 16. 16, 3 and 3, 6 and 2, 8 times 2, 16 hydrogen. We have 2, 4, 6 here. So we only have 10 hydrogens to play with here. So whatever it is that we're going to be looking at between the 2 substances, we must have 4 carbons and 10 hydrogens. And the only way that we can get that is with methane and propene. Yes. Question? Okay. Oh, all right. Is there another question in the chat?
Could it have been What was that?
Or ethene and ethane.
Right.
So that is C2H4 and C2H6. I guess it could have been ethane and ethene. No, but we have ethene already. See, we already have ethene. So it's two different. So that's the only way. Because we have ethene already being produced. So the only way for us to use 4 carbons and 10 hydrogen is methane and propene. All right? Because ethene is already there in the equation. All right, account for the tetravalency, sorry. And although the reason why I am going to do this question is because this falls under the first section of the syllabus, which is one of the topics that they say will be coming on the examination. So I think it's structure and formula. So account for the tetravalency of the carbon atom, 2 marks. Anybody? Why is carbon tetravalent?
You want to answer? Could you raise your hand or unmute your mic and ask and answer?
No one? No one can explain why?
No one is biting, no?
All right, I see something in the chat.
Yes, somebody says the ability to form 4 bonds.
But why?
Right, you see.
Why? Account for, and that is the difference. Oh, I keep forgetting. This is the group who did not do a paper 2 for CAPE last year. Even when the marks look very minimal to you, you need to look at the verb that is given to you in the question. So it says account for, which basically means that you need to give an explanation. You need to tell why. So you can't say that it's the ability to form 4 bonds. Why does it have this ability to form 4 bonds? All right, I see part of, no, you can't just say it has 4 valence electrons. I see part of my answer. Oops. What did I do? I lost it. All right. So, Nikalia, you would have gotten 1 of the 2 marks. Nobody can give me the other one? All right. So you have the unpairing of the 2s2. Please remember that according to the electronic configuration of carbon, carbon should only really be able to form 2 covalent bonds because its electronic configuration is 2s2, 2p2. And the s orbital is filled in that configuration. So what takes place is the unpairing of the 2s2 electrons so that you get 2s1, 2p3, and then you get hybridization taking place. So the 4 orbitals are hybridized to give you 4 sp3 orbitals. So 1 mark for saying that you would unpair the 2s2 electrons and 1 electron enters an empty p orbital. And then the 2nd mark for saying that the 4 orbitals are hybridized to give 4 sp3 orbitals.
Miss, could you repeat the first mark? You said 2s2 electrons are unpaired.
The 2s2 electrons are unpaired and 1 electron enters the empty p orbital.
Okay, thank you, miss.
Miss, could you repeat the whole thing, please? I'm trying to jot it down.
Okay. But remember that you the recording will be available also on YouTube, so you can go back to it. But I'll repeat. The unpairing of the 2s2 electrons and one electron enters the empty p orbital. That's 1 point. The second mark, the 4 orbitals are hybridized to give 4 sp3 orbitals.
Thank you, miss.
Okay. All right. Aqueous bromine will only react with propane in sunlight, but aqueous bromine reacts quickly with propene without sunlight. Using appropriate notation and equations, explain the steps involved in the mechanism of the chemical reaction of aqueous bromine with propane in sunlight, or aqueous bromine with propene without sunlight. So here they've given you a choice. So you can either look at bromine with propane or bromine with propene. Anyone wants to tell me what the steps would be? First with propane. It's 4 marks. Four marks. All right, what are the 3 stages that for propane with bromine? What are the 3 stages that you would have to?
Miss, you'd have initiation, propagation, and then you'd have termination.
All right, so you have initiation, propagation, and termination. All right, so the marks would have been allocated. It's 4 marks, 3 stages. 1 mark for the initiation, so you give 1 initiation equation, 2 marks for propagation, and 1 mark for termination. All right, and when you are doing, all right, let me see if I can quickly put this on the whiteboard. Not my favorite thing, but let's use it. Let me clear it. Clear all joints. All right. So for this, you are going to let me double check what the question asked for. It says, using appropriate notation and equations, explain. When they speak of appropriate notation, they are speaking of, when they speak of appropriate notation, they're speaking of using your curve arrows. So in this case, oops, a half arrow to show that 1 electron goes there, and another half to show that one goes there. Oh my, that's a time. All right, so that would be my initiation. All right, and then, of course, my propagation. What were we looking at? Propane. So I need, let me start from here so that I have enough. All right. So my hydrogens. All right. And this is plus our BR. And this is going to give me my new free radical, which you really should draw out, but for the purpose, so you should draw it out as a displayed formula because they want you to show what is taking place. And this is plus HBr. All right, so this is one propagation, and then you could do another propagation, and that would give you 2 marks. And of course, termination would be any 2 of your free radicals coming together. All right.
Okay, so somebody had given the steps in the chat, and someone else is asking what is taking place with the propene.
Where? Sorry.
I guess the arrows you have at the propene. I don't know. Stania, you want to
Homolytic fission, because remember, you have formation of a new free radical. So you would have to have homolytic fission taking place. So your 1 electron goes to your carbon, 1 electron goes back to the hydrogen, and these two free radicals come together to give you your molecule. So that's how you get a new free radical, single-headed, Terrian, single, not double, single. So all of these are single. All right. Any other question? All right. And the second reaction, the second mechanism looks similar to the mechanism that we would have done previously. So they gave you a choice in the question. In the question, remember they said that you could either do, so using appropriate notation, an equation explain the steps involved in the mechanism of the chemical reaction of aqueous bromine with propane or aqueous bromine with propene. So the mechanism that we did for the previous question, your electrophilic addition is what you would do if you chose. So it was your choice. They were quite nice. They gave you a choice. All right. And then they say name the mechanism of the reaction selected. So if you used propane and bromine, what would be the mechanism? If you use propane and bromine. Propane and bromine. Why am I not getting in the chat? Propane and bromine.
Is somebody saying free radical substitution?
Right, and if I use propene and aqueous bromine, what would be the mechanism?
Electrophilic addition.
Go again, please. You broke up. Go again, please.
Electrophilic addition.
I'm not seeing the chat.
Excuse me, I have a question.
Yes.
I was kicked out of the, well, my laptop died, so I had to rejoin a while ago, but I meant to ask, when you're displaying the propagation step where C3H8 reacts with a bromine radical, you wrote that the products were HBr and the CH3H7 radical, correct?
Yes.
My question is, that could have also gone, the products could have also been the bromo, propene, and an H radical, right?
It could have been, all right, so I had C3H8 and Br.
Yes.
And what did I give you as the, yes, it could have been.
Okay, so
It could have been.
either way.
Yeah.
Okay.
All right, electrophilic addition is correct for those who said, wrote that in the chat. All right, wow, I'm going to be late for my class. All right, describe the observations expected when 1 aqueous bromine is added to liquid heptane. What would you see? Aqueous bromine added to liquid heptane.
Someone says brown to colorless solution.
All right, so you're going to get the change from a brown solution to a colorless solution. All right, acidified potassium permanganate solution is added to liquid heptene without sunlight, they put.
Someone says purple to colorless.
Purple to colorless. And you can, if you write for either one of them, just colorless, you lose a mark. When you're giving color changes, you must give the initial color and then the final color, especially when you see 2 marks allocated. Especially when you see 2 marks allocated. All right, so I'm going to stop here for today. And I am wishing for all of you all the best in your examination. I see evidence that persons have been reviewing. Continue to review, put your best out there. Please remember that for most of you, this is the stepping stone to move on to something else. So next year, you would not be doing CAPE again. So put out your very best, and I'm sure you'll all do very well in the examination.
Right. So students, if there's any lingering question, okay, yes, here's somebody saying they want to see slides 1 and not 1. Slides 1 to 5 before you go. Right. So if you have any lingering questions, there was anything at all that Miss was explaining and you still didn't get it, you can quickly raise your hand and ask the question before you leave. If not, you can continue to tell Miss how thankful you are for her help in this session. All right, so show your appreciation for Mrs. Hall, send in those reactions. All right. Okay. And all the best in your exams as well. The person is asking for slides 1 to 5.
1 to 5 would be my initial slide up to the objectives. Are you talking about 1 to 5 of the actual information?
The person who's requested the slides, please indicate. In the meantime, somebody's asking about they didn't get the last stage of the free radical substitution.
Open your mic, Terrian, and ask the question. What is it you didn't get?
Somebody's asking.
Oh, what came before combustion?
Okay, that's a different person.
All right, bond fission, it was bond fission, and then was it combustion as in combustion under alkanes? Well, bond fission would have been, so speaking of the 2 main types of bond fission for covalent bonds, homolytic and heterolytic. And please remember, I'm going to share the this presentation with Dr. Taylor so that she can email it out. Oh, I didn't show it for the question. No, I just stated that it would have been any 2 of your Any two of your free radicals coming together. So two Br free radical or two propyl free radicals or a propyl with a Br free radical. So any one of those would have given you the mark. All right, any other questions?
Not seeing any at the moment.
All right, and then it was a general combustion. It was a general combustion equation. And then I started alkanes and I did combustion of alkanes. Before that, it would have been the objectives that I would have had.
Okay. All right. There are no other questions. We want to express our appreciation for Mrs. Ellis Hall, who took us through the portion of the organic chemistry for Unit 2. Remember that the entire session is on YouTube, so you can just search for Cape Chemistry Camp, and you'll find the video, and you can watch it again. Someone is asking about when water is added as a nucleophile, does it lose hydrogen?
Yes, it does.
Okay.
Yes, it does. So it loses that hydrogen. Remember, oxygen would love to continue to have its two lone pairs. So it initially forms that dative covalent bond, donating a lone pair, but then it takes the electron from the two electrons from the oxygen hydrogen bond and keep it for itself. So, and gives off that H+ ion.
Okay, great. All right. So let me stop. Okay, thank you very much again, Mrs. Hall.
Yes, I am late for my lecture.
I am so sorry.
No, that's all right.
All right,
I am just, well, I am on time. It's going to be a minute late because
okay.
I need to,
yeah, switch
log
and so
into
on.
it.
Right,
But,
okay, we appreciate your help.
You're welcome. You're welcome. All
Okay,
right.
all right.
And good luck, everyone. Bye, everybody.
Right, blessings to all the best in your exam, students. Okay.